Hi, today we are going to learn how to predict thief names. So we will use Yolo V8 and create an object detection model in order to detect those thieves. You are most welcome to subscribe my channel. So let's start. So let's start with the Yolo V8 installation. So I will leave a file named install YOLOv8.txt that contains all the steps here, so you can run those commands along with my installation. So first of all, let's open a conda environment, and so we type conda, and then it will be better to run it as administrator. So as you can see, here is our command prompt, and first of all let's start with creating the conda environment. So we will type conda create --name. Let's name our environment as Yolo V8 tutorials. Okay, we will do several tutorials using this conda environment. Then we have to choose the Python version. It should be 3.8, and let's run it. Let's click yes. And let's activate the new conda environment. Conda activate, and we should type our name, which is Yolo V8 tutorials. As you can see, this is our current environment. Next, we have to choose the PyTorch environment. So in order to do that, we have to run this command nvcc ---- version, and here is my CUDA version. I installed 11.8, so basically I need to look for a PyTorch version that's suitable for 11.8. So now let's go to the PyTorch website, PyTorch, and instead of downloading the last version, let's go to install previous version. And now, as you can see, for each of those versions there is the relevant or the suitable CUDA environment. For example, version 2.3.0 support 11.8. If we go to previous versions, for example, let's see, I can see that most of them support 11.8, and for example this version 2.00 support 11.7. so if you are looking for earlier ones, for example version 1.13.1 support CUDA 11.6. so this is how you can find the relevant PyTorch for your local installation. As for our tutorial, let's choose this one, 2.3.0. so I have to copy this command. This is the relevant command for installing the PyTorch. So let's copy the command and paste it, and let's run the installation. Let's click yes. Great, finished. Next we have to install the Yolo V8. I prefer for this tutorial to install the Yolo V8.1. So let's copy this command and let's run it here. As you can see, the process running automatically and installing all the relevant Python libraries. After the installation, you should choose the right interpreter in your VS Code. So you have to relaunch your VS Code in order that all the changes will take effect, and then you should click Ctrl Shift and P together and then choose select interpreter, and these are all the current Anaconda environments that exist in my local machine, and I'm looking for this one, the one that we just created, Yolo V8 tutorial. So now my VS Code will work with our new Yolo V8 environment. The next step will be downloading our dataset, and this dataset should be in a Yolo V8 format. So I created another txt instruction file named prepare the data. As you can see here, we have a link for our dataset, and our dataset is dealing with tooth. So let's copy the link for the dataset and let's open another browser tab, and here this is our dataset that contain images of tooth. And as you can see, we have 174 images as train set, 18 for validation set, and 8 images for test set. And if we'll go to the images, you can see that if I will open one of the images, you can see that all the images are already annotated, and they are annotated with different classes. Some are for upper teeth and some for lower teeth. And if I go here, you can see all the classes that were annotated in this specific image. We have 2 images that are categorized as C lower and 2 as C upper, and this is named CL lower and this is CI upper. So all these are categories for locations of teeth. Let's go for another image that you can see that this is the same concept. All the images are already annotated. So basically we are going to create a model that will detect the position or the location of a teeth by using a new and fresh image after the training process. So let's go back to our images. I can also click here for overview of all the dataset, and if I go back to the images, you can see that under these classes I can see all the relevant classes in our dataset. So let's go back here to the dataset, and we would like to download this dataset. Since we are using the Yolo V8 model, we will click here, Yolo V8, and then click download as zip file and click continue. And this will download all the information to our local PC. I already downloaded and extract the zip file, and let me show you here under dataset subfolder. I created a subfolder named teeth2, and here are all the folders. So if, for example, I open the train subfolder and I open the images, you can see that there is a lot of images of teeth. And if I open this specific image, this is the image, and there is also here the name of the image followed with .jpg. But if I will open the labels, all the names of the labels are identical for the images, and the only change is the suffix, which is txt. So this, for example, is the first image. If I open this label that indicates all the categories and all the annotations in the first image, you can see that we have 2 tooths of category 3, 2 tooths of category 5, 2 tooths of category 1, and each one of those tooths has its annotation that indicates the bounding box around of each of those tooth. So what are those categories? What are those numbers? Let's go to our main folder, and we can see there is a data.yaml file. Let's open this and let's open this file. And first of all, we can see that we have 9 categories, and these are the labels for those 9 categories. And the first one is 0, and this is 1, and this is 2, and this is 3. So these are the numbers that indicates the labels for our tools. So if we saw earlier in the label file, we saw, for example, the number 0, that indicates this type of tooth. And very important thing, another issue is where is the train images and where are the validation images and where are the test images. We will change it in the next phase when we indicate all the training process. So it's really important to double check the structure of your folders. This is the main data folder, which contains the data YAML, and under this main folder we should have a train subfolder and a validation subfolder that contains each one of them, the images subfolders and the labels subfolder, as I mentioned earlier. So before you continue to the next step, please double check that your folders are composed of this structure. Okay, let's start with discover our dataset and learn more about it. So we will start with creating a new Python file. Let's call it show one image. It will be our step number 3, and we are going to display one of the images with the bounding boxes. So let's start with importing the necessary modules from the YOLO library and also OpenCV and YAML. Then we will specify the path to the image file that we want to process. Let's take one of those test images. Let's copy the full name of this image, a very long name, and let's add the full path for this image. So this is one of our train image. Now we also need the path for the specific annotation for this image. So we will specify the path for our annotation file, which is corresponding to our image. Great. Next, we will specify the path for our YAML file, which contains the metadata about the datasets, like for example the class names. So here is the full path for our data YAML. Then we will open in the YAML file and load in its content into a Python dictionary. We will name it data. Next, we will extract the label names from the loaded YAML data, and let's print it. We are expecting to see those 9 label names. Great. Let's continue. Now we will start reading the image from the specific file path using OpenCV, and we will also extract the height and the width out of this image. Then we will open the annotation file and read its line, and we will put it on the lines variable. Next, we will initialize an empty list to store the annotations, and we will start iterating through each line in the annotation file. We will split the line into individual components, which are the labels and the coordinates. These are the X, Y, W, and H parameters. Then we are appending the annotation as a tuple to an annotation list. Great. And let's print the result. And let's run it. Great, as you can see, these are the values that store in this list. So it's a category and it's a bounding box. Now we will iterate through each annotations to draw the bounding box and the labels on the image. We will convert the label index to the actual label name using the label underscore names list. Then we will convert the YOLO coordinates to pixel coordinates. So now x1 and y1 will be the left upper corner of the box, and the x2 and y2 should be the right down corner of the box. Let's wait a few more seconds and we will finish creating those coordinates. Now we will draw a rectangle box using the OpenCV library on our image using our calculated pixel coordinates. We will choose a color and the thickness of the rectangle. Next we'll display the label name near the bounding box. As you can see, it will be 5 pixels above the box. Great. And at last, let's display and show our image that contain the bounding box and the labels as well. I have to fix, I have some syntax error here. It should be Y and it should be Y2, of course. Great, let's run it. So this is our image with all the annotations, labels, and the teeth names. Now, let's continue for the next step, which is training our model. But first of all, before writing the Python code, let's go back to our train images. And as you can see, we have here the data YAML that we opened earlier and demonstrate all the 9 classes that are annotated with our images. But another issue, it's very important to put the right path for our train images, validation images, and test images. Test images is not so relevant because it will not participate during the training, but it's really important to put the full path for our train, since we are not running the code from this specific folder. We just indicates the path for those images. So let's copy the full path here. So it is C, datasets, teeth2, train, and images. And we should do both the similar for the validation, valid images, and as I mentioned earlier, the test is not relevant. And don't forget to save the file. Let's continue for coding the training process. So we will create another Python file named train.py, and we will start with importing YOLO module from the ultralytics library, and then we will define the main function that will execute our core logic of the script. Next, we will load the YOLO model with the specific configuration file of the YOLO 8L. L means large. We will choose the large model. As you can see, if we go to the Yolo V8 GitHub library, there are several object detection models. Here are the list. There is a nano, small, medium. We will choose 8L, which indicates the large model. Let's continue. Now we will specify the path for our YAML file that contains the dataset configuration. So this is the full path for this file. And next we will define the folder where the training result will be stored. So let's name it under teeth2, and we will name our variable as project label. Then we will define the name of the experiment for the model. We will name it my teeth model. So basically we will generate a subfolder name my teeth model under teeth2. Next we will set the batch size for the training, and now we will set up all the arguments for the training parameters. So we need to send several arguments like the config file, how many epochs, let's run it on 100 epochs, the project folder, the name of the experiment under the project folder, how many images for each batch. Device mirror 0 means that we will run the GPU card, and validation true means that we will also run validation after each epoch. As mentioned earlier, all the results will be stored under the my teeth model subfolder that would be generated under teeth2. So here we expect to see all the results. Next, we are checking if the script is executed as a main program and calling our main function. Great. So let's run the training. So as you can see here, we loaded the model weights. Now we loaded the 174 train images and the 18 validation images, and we start training. This is the first epoch, and basically we are not going to wait for all the 100 epoch. Let's run it on a fast forward and wait, let's say 10 more seconds, just to double check that everything seems okay, and then I will stop recording and jump directly to our last epoch, and we will start investigating the results. Okay, so after 100 epochs, you can see that the loss is about 0.8, and also you can see the results for each of the categories. So in order to examine the results, let's open our datasets folder, and inside it we generate a my teeth model subfolder that contains all the information. First of all, the weights are stored in the subfolder weights, and there are two files. One contains the last weights and the other contains the best result weights. When we will test our fresh images, we will just test it on our best.pt weight file. And now let's first of all open the results diagram, and let's focus here on the box loss, this one. And as you can see, the line goes down. This good direction means that the training is on the right way. And another file is open the confusion matrix. And as you can see here on down, we have the true values, and here we have the predicted values. And you can see the results is on the diagonal here from the upper left corner to the right down corner. That means that each of the categories is the same as the true values, so the prediction is good as well. Here we have some minor values that there is a difference between the true values and the predicted values, but basically most of the values are here, so it's a good training as well. And let's open one of those files. For example, we would like to see this one that examines the first batch on the predicted images, and here if I enlarge it, you can see that it also discover and detect all the images, and there is a value of how precise is the prediction, and you can see that there are values above 0.8, so it's very good prediction as well. So basically, let's try it now on a new and fresh image. We will choose one of the test images, one of those images that our model never see it before. So let's continue to the next Python code. So now we are on the last page, which is testing our model. Let's create a new Python file. Let's name it predict.py, and basically we will load a new and fresh image out of those test images, and we will try to predict it. So first of all, we will choose one of those images. Let's go to the test images folder. We will choose that one. Let's copy the name, and we will add it to our Python code. Great. So this is the full path for our image. Let's also load the annotation of this image. We will use it only to compare the prediction results and the ground truth. So we will go to the labels folder. We will just double check that there isn't any error with the name of the label. Yeah, great, now it's okay. And let's start with loading our image. Now we will grab the height and the width. And next we are creating a copy of our image for prediction purposes. So we will use the copy function. Then we will specify the path for the train YOLO model file best.pt that contain the best weights of our training. Now we will load the YOLO model with a specific model file. Next, let's set the thresholds for the prediction confidence of 50%. And now we are making predictions on our copied image using the loaded YOLO model. Let's print the results. So this is this results object, and now we will start extracting the information out of these results. Let's start with getting the first element that contains all the information, and we will start with iterating through each detected result and drawing bounding boxes and labels on the image for prediction with the confidence score above the thresholds. So now we are grabbing the information, and we will display only scoring above our 0.5. Then we will draw a rectangle around this object. We will use the x1, y1, x2 and y2 coordinates for drawing our box, we will also choose a color and how thick would be the rectangle. Then we will use the put text in order to display the label name out of the class ID. Once again, we will choose a color and also the thickness of the text and the type of the text. Now, after displaying the detection, the prediction results, let's display the ground truth. So once again, we will create another copy of our image, and next we will open the annotation files that contain the ground truth, and we will read all its lines. Now we will initialize an empty list to store the annotations, and next we will iterate through each line in the annotation files and extract the labels and the coordinates. Now we will run another iteration through each annotation to draw the bounding box and the labels on the image for the ground truth. Next, we will convert the label index to the actual label name using the model's labels. Now we will convert the YOLO coordinates to pixel coordinates. And since we done it before, let's copy the code from our previous Python code. So let's copy all these coordinates and also the rectangle and the put box function. We have to do some adjustments, like the name of our image, and also the label name is different. And let's display our images. So first of all, let's display our prediction image that contains all the prediction boxes and labels. And let's display the ground truth with the real annotations. And let's also display the original image as is without any bounding boxes and text. I have to fix this one. It should be annotation. And also I am show, that's right. And let's fix this one. It should be img true in both functions. And let's run it. Let's rearrange the results. On the right side it's the prediction, on the left side it's the ground truth. As you can see, the prediction results and the truth results are mostly similar. I hope you enjoyed this tutorial. You're most welcome to subscribe my channel. See you on my next videos. Bye bye.